So in this video, we're going to look at an additional example with Hess's law and get some practice with it. And this is an example of why this is so powerful. Because our first equation we're looking at is a combustion reaction with methane. But it's not a typical combustion reaction. It is an incomplete combustion because instead of our typical products of carbon dioxide and water, we instead have carbon monoxide. Carbon monoxide is a poison, and we want to, be able to control how much it's produced. We'd rather get zero of it if possible, but we need to understand this reaction and its properties. But it's a difficult reaction to measure because it's an incomplete combustion. If you just combust methane, most of it's going to go according to our usual reaction with oxygen to form carbon dioxide and water. So what we can do is use two reactions that we can measure easily, which is the combustion of methane. So that's reaction 2 here is methane plus oxygen to form carbon dioxide and water. And we know the enthalpy of this reaction. It's a highly exothermic reaction. And we can also use equation 3, which is take carbon monoxide, react with oxygen, do a combustion reaction, and form carbon dioxide. So we know what reaction we want. That's equation 1. And we'd like to use equation 2 and 3 to find out what the enthalpy of equation 1 is. So that's our goal in this problem. So let's start by looking at a couple things. So first, in our desired equation, right here, we have methane as one of our reactants. And if we look in equation 2 and 3, methane only shows up on the reactant side of equation 2. Similarly, if we look at water, H2O here, it also only shows up in equation 2 as a product. What about our carbon monoxide? So that I've already highlighted it in red here. Well, carbon monoxide, if we look in equation 2 and 3, the only place it shows up is equation 3. But it shows up on the wrong side of the equation. It's on the reactant side in equation 3, but on the product side in equation 2. And so we can start to use these as clues to figure out what do we need to do with these reactions. Oxygen and water is pretty straightforward, but and carbon dioxide also shows up in both equation 2 and 3, but is not present in equation 1. So that's going to need to cancel out at some point too. All this is a clue. All these are clues, and this is a puzzle we're trying to work out. I like to think this is a puzzle. So what information do we know? Well, we know equation 2 needs to not flip around. We need to not reverse it because it already has methane on the right side of the equation, on the reactant side of the equation, and it already has water on the product side. And those aren't present in equation 3. So we can leave we don't need to reverse equation 2. Equation 3, on the other hand, has stuff on the wrong side of the equation. We need carbon monoxide specifically to be on the product side. And this is the only place it shows up in either equation 2 or 3, so we're going to have to swap those around. So let's go ahead and write these equations with those swaps done. So we'll leave equation 2 as is. I'm going to leave off the states of matter just to make it a little bit shorter to write. So equation 2 we'll leave as is. And then equation 3 we're going to flip around. So we're going to reverse it. And as we do this, we want to keep track of what we've done so that we can do the same thing when we add together the enthalpies using the principle of Hess's law. All right, so our reactants now are 2CO2, and our products are 2CO plus O2. Okay, great. Now, there's one more thing if we go back up to our original equation. The coefficients don't match up. So we need 2 methanes, but we only have 1 in equation 2, and we need 4 waters, but we only have 2 in equation 2. So we're going to have to multiply equation 2 by 2 to get the correct coefficients for these. And we'll see if that works out in getting the correct coefficients for everything else. So we need to multiply by 2. Right, so this 2CH4, 4, 2, and 4. And now let's add these together and make sure we get the original equation we want. So we're just going to carry everything down and then cancel out things that show up on both sides of the equation. So we have 2CH4 plus 4O2 plus 2CO2 produces 2CO2 plus 4H2O plus 2CO plus O2. And here I'm just copying down whatever's on the left-hand side of the arrow stays on the left-hand side of the arrow. Whatever's on the right-hand side of the arrow stays on the right-hand side of the arrow. And now we want to look and see, is there anything that shows up on both sides of the equation? Let's use a different color. Let's use pink. So I immediately see 2CO2 shows up on both sides of the equation, so we can cancel that out. And let's switch color. We'll use orange this time. And we can also see that O2 shows up on both sides of the equation. But these don't have the same coefficients. But we can see for every, and it's similar to like an algebraic equation, if we have 1 O2 on this side and 4 on this side, we can cancel out this 1 and subtract 1 from over here, and we'll get 3 left over. So this 4 becomes a 3. So after doing that, let's clean this up, rewrite this. We get 2CH4 plus 3O2 produces 4H2O plus 2CO. All right, and does that match our original equation we're trying to get? 2CH4, 3O2, 2CO, 4H2O. Yep, everything is there. And everything, I left them off, but everything's all gas phase here, so they're all in the correct states of matter. That is one thing to also be sure about. Okay, so that means we can take our enthalpies, right? So this was delta H2 and delta H3. We can take our enthalpies and do the same thing we did to the reactions. So delta H2, we need to multiply by 2. And delta H3, we need to subtract instead of add because we reversed it. And that will be equal to delta H1. So now we can go back up and grab the values for delta H2 and 3, negative 802 kilojoules for delta H2, negative 566 for delta H3. We can go ahead and plug those into this equation that we have down here. So delta H1 is equal to 2 times delta H2 was negative 802 kilojoules, and minus negative, so this is going to end up being positive, 566 kilojoules. Right, if we go ahead and do that math, we get delta H1 is equal to negative 1038 kilojoules. Just double check on my calculator real quick that we've done that correctly. That looks about right. So 2 times negative 802 plus 566 gives us 1038. All right, so that's great. So that's an example of how you can do a Hess's law problem. It's like a little puzzle. You got to figure out to get all the reactants in the right place, all the products in the right place, and then keep track of what you did so that you can do that to the enthalpies as well.